first technique we briefly discussed this even yesterday, right? Sake of completion we will write it down. So mathematical modeling is the first way to analyze, understand the performance of a given system. And the second is simulation. Again there is analog simulation, discrete simulation. Today we talk mostly about computer based simulations. And in particular we will talk about discrete event simulation. And then of course, right, the third aspect is to implement, right, implementation based So the book actually calls this simply measurement, but we do measurement in any, whether it is simulation also we measure. So therefore I have simply added this term implementation. You basically implement it in a real system, right? This is a practical implementation. For example, some cache coherence protocol that you have come up with, you should be able to, you can do analysis, simulation or mathematical modeling, right? And we sometimes also use the term, right, analytical modeling here. So if you have taken ADSA or DSA, right, or data structures algorithms, probably have done some of these things, right, in your labs. So you have done in class, you have done your theoretical analysis of the algorithms, then we didn't do this, you simply went straight away to implementation because it was mostly, right, straightforward algorithms. It's not a complex system that you are trying to simulate, okay. And then implementation, but measurements you probably maybe a couple of values of sizes of the list, but mostly worried about correctness, right, functionality is what you worried about than scalability of the system itself, okay. So we will talk a little bit about the nature or the kind of task that is involved in a mathematical modeling system, okay. So what comes to mind, right, what are the different things involved, and is it hard, easy, time consuming, accurate, right? Reflect on all those things, let me know which is. So is math modeling easy or hard?
It's
Hard, right? It's interesting because only now we start kind of going away from math modeling. Anytime somebody builds a system, either you implement it or simulate it and then you are done. Nobody really wants to go to the analytical part of it. But 20-30 years ago, right, this was not a real option. Computer based simulations were not really around. If you look at a lot of the early papers in even networks, right, I will use that as an example. Most of the early papers were trying to do some sort of math modeling, right. You had to have a math model if you had to have a good paper, but then that is not the end of it. Somebody actually has to build the system, right. Why was TCP/IP successful? Because somebody built it, made it part of BSD and made it available to everybody, right. So it was mostly these two were the traditional options in those days for researchers. Now this is harder. If I suddenly tell you go build a wide area network and test your routing protocols on that, you simply cannot do that, right. Even now it is hard. Even today we will see, I have seen cloud computing based experiments, right. They said I have devised this new algorithm for allocating resources on the cloud, and then okay, where is your cloud? I have 4 machines on a LAN, right, that is my cloud. That is not a cloud. Where did you emulate the cloud, right? You should actually have accounts elsewhere or put your machines elsewhere and somehow access that. So implementation has always been hard, but this has always been easy. So if you look at a lot of the early work in computer systems and so on, they really depended upon mathematical modeling, right. But today we are sort of veering away from that because we know that there is an option. Otherwise you could have simply proposed an algorithm and said I am done, you won't be able to finish your work and go anywhere, right. So either you implement it or you analyze it. So so therefore this is, I would say, harder, right. So the skill set involved is you need to have some knowledge of several math techniques, right. We are going to see only some of those in this class. Markov chains, models and so on, but there is a wide variety of analysis techniques, modeling techniques that are there. And usually what we do is we have one tool. I know Markov chains, therefore everything is a Markov chain, right? Whatever system you give me is a Markov chain. I simply draw a Markov chain for everything. So we have to be willing to go beyond. Even I have stopped. I didn't go beyond Markov and semi Markov, but that's why you have a class of researchers that try to keep on coming with new techniques, right? Those are the performance evaluation researchers. There are people try to come up with new math models, and those who try to use them and show us how to use them. And then once somebody shows how to use them, we simply use that same model over and over again. Right? This classic example is in the case of like optical networks. There is this traffic requests come in, light paths come in, they get established or they don't get established. So there is a way to calculate the blocking probability. So the blocking probability, most of us were initially doing simulation based, right? Simulate and then show the results, or do an ILP, integer linear programming formulation. This is a design problem, right? What is the performance of the system, or how do you design the light paths and so on. And then I guess in 1999, 2000 a paper came along that showed how to do blocking probability computation. It was fairly intricate probability and probability use to actually do this calculation. So once they did that, then that became the tradition. Everybody else would simply use that same model and start computing things the same way, right? So now and then people come and show you how things can be done differently, but otherwise we stick to our known set of tools, right? And then keep using that over and over again. So this the skill set, right, is purely mathematical, right? And if you go to a math school, they will say that this is no big deal, we do this all the time. When we come to computer science, we will say, well, we can do some of it but not all of it, right? So the skill set required is purely mathematical. But what else? What other features, right? Is it good, is it bad? So we said it's hard, okay, forget it. Let's say you have to do math modeling, I said nothing doing, right? Without that you cannot get your PhD. Usually for PhD students we insist on that, right, that you better do a math model of your system, otherwise there is no rigor. Why does math model help you? Sometimes the math modeling helps you abstract the system away, right? You are looking at the system at a very high level, not at a detailed level. Detail level, worry about all the variables, all the files that you have to include, right, at the level of implementation. Sometimes that is irrelevant. You really want to abstract the system away at a very high level. So it gives you a bird's eye view of the system, right? So that is the good point about it. So you have a very high level abstraction of the system.
Should we call it a high level, or it should be a lower level abstraction?
What do you mean by high level? You are, let's say you are looking at queuing scheduling algorithm, right, in an operating system, and you have this multi-level feedback queue, if you remember AM, right, where you start off with some very low quantum, then you keep jumping to different queues and so on, right, and then you go to IO queues also, right, you have the CPU queue, you go to some IO queue and so on. Now if you look at it from a real system point of view, you will start worrying about how do I build these queues, should I use linked list, doubly linked list and all that stuff. Here if I look at it as a math model, you want to know what is the throughput of the system, how many jobs, right, per unit time can the system complete. You simply view the system as a collection of networks of queues. It is simply a set of queues and that is about it. You do not worry about all the lower level details of implementation.
Once we are doing math modeling, we will not be putting in various variables or various parameters.
Yes, so that is true. Yeah, that is why it is a very abstract model, which is good to start with. You do not worry about the details initially, because you want to get an approximate understanding of the behavior of the system. To get the approximate behavior, you start with a very I would say gross abstraction, not a detailed abstraction, right.
But you may have certainly some gaps where you actually try to abstract something which
true.
Your approximations could go wrong.
Yes, yes. So that is why this is a starting point. So mostly they use this as a starting point, right. Even we talked about sorting too, you have two different algorithms, both of them saying n log n, which is better, right. Why do people use quicksort all the time? You tell me, why is quicksort used more often? Right, quicksort is used more often than the others, even though there are others. Merge sort is also n log n, right. Why is quicksort used more often? Yeah, so that how did you know that? That is either you do analysis or you can also verify that empirically, right. So you have both verifications to do. But you knew that I do not want to look at n squared algorithms, right. This eliminates your n squared algorithm space, all those naive algorithms are gone, right. So therefore this helps you narrow down to a set of most probable systems or techniques to use. So that loss is there. So that is why you lose. So this very high level abstraction is both a positive and a negative. Positive is that it lets you focus on the main characteristics, not on the details, but sometimes details are also important. So you lose the details which you have to capture with the next level, which is simulation based systems and so on, right. So this very high level abstract, right, makes lots of assumptions. So you assume, right, you always say assume that, and then you say, let us say I want you to find out what is the average delay of customers coming to the State Bank or some bank, right, teller, and either you sit there daily and measure, or if somebody tells you that, okay, I sat there for an hour, I think about 10 customers per hour came, right, okay, good. What is the average service time per customer? I mean, okay, about 5 minutes per customer is the average I saw for this 1 hour. Then you would say, okay, tell me what is the average delay, right. So you can simply go to a system with a known closed form solution, which is say MM1 or MG1 and so on, right. If you make those assumptions, you first of all say that I assume that the arrival process coming to this queue is Poisson, right. Nobody ever verify that it is Poisson, it could need not be Poisson, but that is a convenient assumption you make because there are closed form solutions, right. So wherever you find convenient assumptions about the system, right, characterization, you simply take those simply to get your closed form solutions, right. So therefore that need not be holding true with what your actual system is. Nobody even knows whether it is Poisson or not, right. We just say that, well, conveniently I will assume that it is Poisson. Many things you simply assume Poisson. The networks, there was a long fight, right. People said no, calls are no longer Poisson, it is, right, something else, it is Markov modulated Poisson, right, or self similar traffic, all those things came about. But fundamentally if I want, just tell me approximately what the delay will be, right. Should I put 10 servers or 20 servers? Now for that sometimes MM1 is good enough, right, your basic queuing models are good enough. So you start from there and then you start going into more detail. So you do make a lot of assumptions, right, which does not fully represent the system behavior. So that is a negative. And so that is also, because of that your results are also not accurate, right. Your results are only asymptotic results many times. It gives you, sometimes it is accurate. If you really system is MM1, we will verify this. If I really simulate an exponential arrival and an exponential or a Poisson arrival and exponential distribution time, you will get those closed form solutions, right. You actually simulate those, you can verify that, but the question is whether the system really behaves with those kind of assumptions, right. So the results are mostly, right, the results are asymptotic, right, not very accurate. So loss of accuracy is there because we know assumptions are there, but what else comes to mind with math modeling? You may not be able to get very detailed performance results. Yes. Yes, outliers may not be captured. Yes. So you may not be able to, yeah, some of those things that we saw many times when you look at this math plots, there are simple equations. You simply plot them and say here is a nice smooth curve, right? And for example, right, you are actually trying to plot the inter-arrival times, right, of packets coming to a system. If I have an exponential model, it will be simply something like this, right. This is the probability. Let us say you are capturing the probability of actually packets coming to the system. It will be something of this. So packets of length this have, right, we actually do a CDF, but let us say that this is some sort of curve that represents, right, something that your probability of something that you are measuring. So this would be your math model that says this is the expected probability for these various things, but realistically your points might fall, right, all over the place. There could be one guy there, could be one guy here, and so on. I could run simulation, right, with different values on the x axis, and I find that this is actually what I am getting by simulation, by experimentation. So yeah, those outliers are lost. So some detailed analysis is not there, right, that is another disadvantage. And also if I want to look at say per user throughput, let us look at Aloha as a classic example, right. If I use, I can, let us say throughput of Aloha, right, I can simply represent by this formula. G is the offered load and e power minus g, so E is your E, right, that we know from math, and so this is the offered load in terms of packets per second, and this is the actual realized throughput by the system. This is a very simple, this is good enough for me to know that my, so what will be if I plot this curve, right, what will it look like? So this is G, the load that we talked about, right. This is load on this axis, right, and this is the throughput measured on this axis. What will it look like? You can verify, right, increase and decrease. And the maximum again you can find out, right, differentiate this, you find max when G equals 1, which is therefore the maximum throughput is 1 over E, and that is 0.368 and so on, right. So this is your 0.36, that is seen when G equals 1. So beyond offered load of 1, which means if I offer more than 1 packet per second across all the users, this is cumulative load offered by all the users of a Aloha system. If I do that, then the system starts dipping, right. So this is what I would get from a mathematical model. If I suddenly ask you, okay, this is total throughput, how about each user's throughput, right. See what can happen in Aloha and other cases too, you have the so called capture, right. I am interested in what is the throughput seen by each of the 50 users in the system across this entire simulation or this some time span. You might find there are problems with that, right. It is possible that one user has pretty much hogged the channel and got all the throughput, others have not got any throughput. If I simply list the throughput seen by the different users, one will be very high, others could be very low, right. If I just plot the throughput per user on the graph. Now that kind of detail I will not get from a math model. If I really want to see per user throughput, that is lost. Sometimes you won't be able to see this capture effect in a mathematical model like this, so that accuracy is gone. Or if I want to say what if I vary the load per user, right, some users are 0.25 packets per second, some are 0.5, some are 0.8 and so on, what will be the system behavior? Mathematical model will say, well, can't do anything about that, I only have this one formula, right, I will simply keep, you give me value of G, I will plot this curve for you, that is about it. So that again is lost, it is not really possible unless you do even more intricate modeling, right. So you sometimes just have this very high level picture, right. It simply tells you at a, like I said, bird's eye view where the scheme will perform better or worse than some of the other systems. Okay. So that detailed, right, asymptotic, not very accurate, some of these things are also captured, right, outliers are lost, very gross or very fine level details within the simulation which you can measure, very fine measurements cannot be done, right. And let us say what is the variance, if I say what is the variance of delay for a particular packet, right, for each user's delay what is the variance, that you may not be able to get from this particular analysis. Okay. So that is a general characterization of what math modeling does, but we always usually like to start with math models because it gets you to think about the system, right, little bit more rigorously. You try to model a system, you find that some rigor is added into the way you look at the system, the way you represent the system, the way you define the system and so on. So that is a nice part about your math modeling, right, it adds rigor to your thinking process. Okay. So now we come to favorite discrete event simulation. So we all know what simulation is about, it is representing a system in the computer using some sort of modeling language, right, several modeling languages out there, and simulation is not just our computer systems, it could be even like a nuclear plant simulation, you can do that, right, people do financial simulations, right, the people do this climate simulation also, lots of things they try to do, right, they said that there will be all those incorrect, some of those predictions happen when you use incorrect simulation models, right, so we will come to that later on, but in general you can capture, you define. So this represents, right, so this is almost a so real world view of the system, right. So you could actually look at your simulation as an exercise that precedes implementation, because many times whatever code, all the logic that you implement in simulation can be directly imported to, if it is a C or if it is hardware then you have to recode and so on, but in general it gives you, right, so your system is modeled as a set of interacting So you view the system as a collection of subsystems, you can implement those subsystems. Within the subsystems you will have your objects and so on, right, just like your regular software engineering project where you decompose the system and then identify what the objects are and so on, right. And these objects in turn will emulate your system, real system behavior, subcomponent behavior, component behavior, all that will be. And depending on, right, where you want to draw the line, you have various levels of abstraction possible. So you can make your system very detailed, you can make your system very a little bit below or a little bit more detailed than analysis, but not very detailed. Okay. So as an example, you are, let us say, developing a new scheduling algorithm for some wireless network, right. So you can simply focus only on the scheduling part of your system, simply say I am going to arbitrarily generate requests, they are of these different types and different priorities, and here is my scheduling algorithm. I will, right, just see how my scheduling algorithm allocates slots to these different users based on whatever factors, the amount of traffic they have been allocated so far, current priority levels, total request and cost and so on, right, quality of service and things like that. So that is a very, just looking at the scheduling algorithm alone, right, that level of abstraction is possible. But then you might say that, wait a minute, this is not enough, I really want to see how this works with say TCP and IP running in the system. So then you have to go and implement above your scheduling algorithm the other network layer protocol stack. You have to implement IP, TCP, or you go to NS2 and just use NS2 or whatever features that it offers. So you can just use that, right. Then there is one more level of abstraction, you are looking at the layers above in the protocol stack, but then you say, you know what, there is so much of channel modeling that is needed, right. You say the wireless channel, I am simply assuming this to be a pipe that will either drop a packet, right, or send a packet with some probability that I choose, but I really want to model the channel also, right. Wireless channel could be simply a CSMA channel, right, with some the carrier sensing and all that, or it could be even more intricate, right, what kind of fading is there, is it Rayleigh fading model or some your log normal fading model, right. So you have to start thinking about even those also start coming to the picture, then you say I have this full end-to-end system, right, and then if you do simulations and present it, you will be, the results will be much more appreciated, okay. So that is where your varying levels of abstraction come in, but there also comes in with the price, right, this level of too much of detail sometimes, because now your systems have too many subsystems interacting with each other, right. You might suddenly find that no packets are getting through, then you start scratching your head, wait a minute, until only scheduling was there things were so perfect, now I put this wireless channel model, I thought it will work well, but now no packets are going through, then you have to start looking at the parameters of the wireless channel, maybe you set your transmit power levels very low, therefore no packets were going through, if you set it at 0.1 milliwatt you find that nothing is going through, and your distance between the base station and you set is like 2 kilometers or something like that. So adding detail gives you more results, but you better know how to set those parameters, right. So configuration of parameters becomes even more important when you start bringing in other systems together, because sometimes those systems are things that you did not write yourself, right. It is fashionable to always go to NS2, get WiMAX, combine them together and run it, but nobody really goes and actually, or not nobody, people, you have to go and actually start checking what those default values are and why results are sometimes not showing up, right. So the different parameters will change the way that your output is going to be, and this we have experienced one, right, practically with using OpNet, which OpNet is one of those paid commercial software that we pay fairly large amount for, and OpNet has this entire stack from generating video traffic, you can generate video sources, voice over IP, everything can be generated at great detail, and then you can send the packets over the wireless channel, measure it and so on, right. But the number of bugs that are there, right, now this becomes a very large system. So where simulation was supposed to be useful is now suddenly becoming a simple regular software engineering assignment where there are too many subsystems that you do not know what is going on, right, and you are simply trying to guess based on the APIs what they would do, and without the source code sometimes it is impossible to debug when failures take place. So that is something that you have to watch for, but the nice thing is you can go to various levels of abstraction, right. You can even look at a CPU, you can simply say CPU is simply my box, right, I can simply emulate CPU instructions that says add, just to add means I will emulate add as it is in the simulator, we have emulators today. Then you say no, I want to go one level further, I want to show even internally what the registers are like, then you want to go further saying no, let us even look at add this caching, right. So for memory simply I get data, I store data, you can even expand memory to its various levels, right, on secondary memory, main memory, cache, and different levels of cache and so on. So that is the good thing about simulation, levels of abstraction, but it also comes with a cost that you better know, right, what happens at the different levels of abstraction. Okay. Anything else about simulation? So I can also do very detailed performance monitoring, right, I can go into every node, I can look at, since everything is programmed, right, I can go in, and if you look at ARPANET for example, the number of metrics it gives you is mind boggling, right, it's a long list of metrics and sometimes they are also incorrect, and we have to figure out why they are incorrect. Like maybe for example in voice calls there is something called mean opinion score that ARPANET was giving us, and the numbers made no sense. The calls are going through in the sense that the packets are getting delivered, but the MOS scores were very low, right, out of scale of 1 to 5 they were giving it as 3. Then we found that there is some mistake in the way it computes the mean opinion score. So that is, but at least we have the option of digging into very very fine levels of performance, right. So we can get fine grained performance metrics can be measured. So far we are saying all the good things about it, right. So what are the bad things or negative things about using simulation? It's prone to coding errors.
Lot of assumptions. We make lot of assumptions.
You will make some more, you will be, the assumptions in the system will be more relaxed compared to mathematical modeling, but where the assumptions would fail is it might not really capture what goes on a real system, right. So because in real system there will be a lot of other things happening, right, that is you know you really cannot capture. For example, trying to measure some routing algorithm, right, or some scheduling algorithm in the backbone, you never know what is going to be the instantaneous load on the backbone router, right, how many connections are coming in, and depending on that your performance results will vary. So you still only have set of representative set of results, right. Simulation again gives you only trends but not real values. You cannot say in simulation I got 2 seconds as the delay, therefore in real life it should be 2 seconds, that is right, that is too much of an extension. So the real life is not fully captured, real life environment is not fully captured in the simulation. Simulation is a controlled environment, lots of things are under our control, pretty much everything is under our control, right. Whereas if you say that, for example, simple thing, virus channel modeling, you say I am modeling it with this fading channel, right, you have this nice set of equations, you put them in MATLAB, and then you go to the system and you find that measurements there are completely unrelated to what you thought, right, where this model that you had so hardly put together or put together so hard with great difficulty. So there is the assumptions right are better than what you would do in case of analysis, but they still do not capture reality, right. So that is the one serious problem. What else? I said coding errors, right. So if your system is prone to coding errors, and many times I have seen my own student for the past 6 months, he has come to me with 4 or 5 sets of results, right, MS student, and each time I found a coding error. I found that this is why, because the results were not matching what we expected, right. Some of the delays are not, some idle time measured is either microseconds, that is not true, it should be nanoseconds, and therefore something is wrong. So we have to go back and revisit over and over again. So you cannot really be satisfied that your code is actually working correctly or not, because there is so much randomness. If it is a sorting algorithm, you know at the end of it I can simply verify, right, run a check to say okay, yes, this is indeed working correctly, no issues at all. Whereas if it is a more complex system that is being modeled, then you will never know whether the results are correct or not. Okay, if your system says delay is 3.52 milliseconds, here is an implementation of the queuing system, did something is, how do I trust that it is indeed 2.52 milliseconds, right. So that is where you have to verify the code and also look for other ways to validate your code. One is to make sure that the numbers from simulation, your implementation is more or less accurate. At the same time you need some other way to make sure that your values are correct, and that is where analysis comes in, right. So you use math analysis as a way to substantiate your simulation results. So many times you will see plots that compare simulation and analysis, and then they should be close to each other. They will not be exactly the same, but at least the trend should be more or less close to each other, right. So therefore this still, right, so your error, the issues are coding errors, and it does not capture or real world whatever environments, right, and it is right. How do we trust the results? So for that we should validate with, and this is again to some extent so they serve a mutually right beneficial purpose, that math models can be verified by simulation and vice versa.
Generally, your simulations are done based assuming your system as a model system, right? And then how do you go back again and to your math model and then compare your results?
Okay, well, let's look at this queuing as an example, right? In queuing, I simply do my Markov chain analysis and I use my birth rate process and say delay equals 1 over mu minus lambda, right? That is what my math model tells. I implement this in a real system where I actually generate packets, where I am actually modeling the behavior of the system. Here only capturing, right? In the math model, I am not really capturing that. Maybe in like, I mean, even if you look at your viral channel models, right? Your channel model is based on some formula that you use and says that at this point in time, right? This is the probability that this, bit will be flipped and so on, right? This will be the amount of noise in the system, and therefore there is a certain probability. Simply add noise and then do it, right? Do a probability flip there and say whether a bit is going to be changed to 1 or 0 or vice versa. But whereas we go to a real system in simulation also, actually you are only going to do that. So from math to simulation, yes, in that case, in some cases you are simply using the math model as is, but in some cases when you really go to measuring on the field, then that's a totally different, right? There your noise is, everything is not controlled by you at all. So some parts of it, yes, you are simply using the math model also in the simulation where there is no cross validation possible. Only when you go to the real system, right, you would know. So in physics again, you have a theory that says this is the way I expect the system should behave, then you have experiments that show that whether your model is correct or not, and they keep changing those models. So depending on which aspect of the system is modeled, if your some parts of your simulation is also based on the math model of say channel or some other system, then yes, the same errors will propagate. But where you can model elsewhere but actually implement here, right, in simulation, then you will be able to differentiate. The third part is experimentation, which I guess not much to say about. You all know how difficult it is. This is actually the hardest, right? So we say implementation. We use the term whatever test bed sometimes, or right, if it is a large scale system, it is a small system implementation. There are several terms. Sometimes people also say experimental results, right, where by experimental they mean that they actually built the system. Different terms you would find, right? We do experiments with everything is an experiment, whether it's simulation or real life, but they would use the term experimental results are present in this paper, which means actually they have built a system, right, and shown some results from that. So what is okay? What are the pros and cons of experimentation or implementation? Takes time, right? Now you have to worry about lot of details, getting your system integrated, getting all those header files put together, all the packages working correctly. So it takes much longer to do implementation. What else?
But it capture all parameters. It's a real world system.
Yes, so it will be operating in a real environment, right? Even that too, sometimes you will never know, right? In the lab, you might be. I used to do this. We had a system for doing zip code recognition or pin code recognition, where in the lab everything worked beautifully, right? Because we are fed images, and then you take it out to the field trial where the sponsor USPS Postal Service was giving some images, the system crashed. It does. I mean, it should have not crashed. Simply it said not given an answer, the system crashed, and I wrote the system. But anyway. So there is sometimes you are even in an experiment, you are still doing a lab experiment, right? It is not exactly a real world experiment. So whatever works well in the lab might not work well in the real world. When you say for a web server, for example, right, web server, in the lab you will be testing with all your local load, it works perfectly. The once you open it out to the web, system simply starts crashing for various reasons, right? Incompatibilities or just functional implementation errors and so on. Okay, but those are, but you need that. If you really want to take your product to your system to become a product, then you have to go into that, right? So one, it takes harder, is definitely right more time consuming. So most time consuming of these three is that. And the second is you would usually find that when you go to experiments, you always try to implement really simple algorithms, right. You leave all the complex algorithms, complex mechanisms out, because especially in prototypes, when you go to a real system, then you have to add all those bells and whistles. So that is one. From the time and cost involved, it is fairly high. In terms of results, is it more accurate or less accurate? More accurate. Well, actually it is probably as bad as simulation too. You really can't say that you're, because whatever errors are there in simulation, right, we think about coding errors in simulation, coding errors can be also in your system. So your results here will be a little bit more believable, but you should not think that this is indeed accurate. Sometimes you will find when an experiment that there will be a lot of variations in the measured results because of variations load, variations in other background traffic or whatever it is, right, in the system. So it is little bit more believable, but I would not say that it is the most accurate, right, because all those errors still also propagate. So, but you generally, it is more easy to sell a system with an implementation, right. If you had, when Google implemented the PageRank algorithm, they were probably able to show that, see, this works better than whatever searching algorithms out there, and therefore you should try to market the system and so on, right. So, so but it definitely gives you much more insight into the system and behavior and so on. And in terms of results, right, when if I want to vary umpteen parameters, I can do that very easily in my simulation environment, right. The advisor will say, okay, vary all these n values, try this for another 10 values and see what happens. Okay, fine. In simulation, because in simulation sometimes your time is constrained, right. I mean you are simulating it for say 5 minutes of system time, which is taking a few hours to run and so on. So you can vary parameters at will in the simulated environment. In a real environment you can, but it is going to be even more time consuming. So mostly you will find that in a simulated paper there will be like simulation based paper 20-30 graphs, does not matter, vary and get all those graphs put together. You go to a test bed based paper, you will find some one table, that is all. We measured, it works, here is the measurements, I am done, right, because it is finally shown to be working. So usually it takes much more time to get a lot more results out of the system, but just mostly a matter of time. So that is why you do all the analysis with all the variables, trying to figure out what are the factors affecting the system. You find out which are the more important ones and you focus on that. When you are trying to do the analysis with experimentation, you try to do that. Okay. So that is the.
So but implementation based method will actually tell me where my error was. Like I tried to implement something and I found the desired result is not coming as what I predicted in mathematical modeling.
True.
Then only I will come to know, okay, something I have done
Yes,
wrong.
yes. So it is almost like a feedback cycle, that you have your model, you implement, and then you find that you have to go back and change your assumptions too. Yes, you find that somehow the traffic is no longer Poisson, it is some other distribution, therefore I have to go and change that to some other model. Yes, I am not saying the experimentation is inaccurate, but you have to be watchful about even experimental results, that you should not trust that completely. You should use, again you should validate that with what your system tells you, with your other two systems tell you, right. If there is a big discrepancy, let us say in throughput and so on, then either it is purely environment dependent, something in the environment which is not captured in those two models is what is causing it, or it may be something wrong with implementation itself, right. So it is, there is not like a magical bullet that says okay one is better than the other, but all these three systems usually tend to be done together, or right, at least two of those should be there, so that you have a good amount of faith. If you only have implementation, then sometimes you may find that there are too many system based things, right. For example, the amount of memory you give on your system, if you are doing it on a virtual box, and you set your virtual box to have only 500 megabytes or so, and then you run your testing on that 500 MB system and you say, well, this is very slow, this algorithm is very bad, you port it to a 4 GB system, then suddenly that the system is better. If you did not think about that fact, then you missed that, right. So you have to think about those also, right. What is the environment, if there is anything in the environment that is causing the system to behave differently from how it behaved in the other two methods. Okay, so these are the three high level description of the techniques. We will next look at some of the common performance metrics, and that will pretty much bring us to the end of chapter 3, and then that is the end of all the introductory material. Then we will start getting into random variables and so on next week. Okay. So commonly used performance metrics, right. So when you think of performance metrics for a system, you think about all the services that the system offers, whatever it is, delivering a packet, doing some computation, right, something, and then the expected outcome for that. So if it's a routing simulation, then the user generates a packet, gives it to the TCP layer. You expect that the network will, right, your TCP model, simulation model says I will take care of all the necessary behavior that will deliver this packet to the end node, which includes queuing, intermediate routers, dequeuing, and finally getting delivered to the end node. So you talk about services and outcomes, right. So that is this when we listed the 10 things to do for doing performance evaluation, this is one of them, right. What are the services offered by the system and what are the expected outcomes of the services. So this is more or less your requirement. So you start here, right, and in general the outcomes, right, for many cases is when you request a service, either there are three possibilities when you request a service from a system, right. And this is not only system level, even subsystem level, right. Some subcomponent also might be doing certain things. So you will have to define, right, for each subsystem, each subcomponent, some of these things. So when a service is requested, there are three things that can happen. One, it is done correctly. Second, it is done but incorrectly. And third, it is not done at all. Your request was rejected for whatever reason. Now this will make sense in some systems, it will not make sense in some other. If you are talking about a sorting algorithm, it will either sort or not sort, there is no question of, right, that the system did not get to the, your system might crash if you give it a very large list of say 2 million entries, your system crashed, then that is an example of it did not get done, right. That is because there was a memory leak in your system. So that is a functional issue there. From a network point of view, it is related to capacity and errors and so on, right. So if I give a packet to a router, either it forwards it or it does not forward it. If it does not forward it, it simply means that the packet got dropped, right, because the buffer got full. So therefore there are some capacity constraints that caused this to happen. So what is the problem, right, or maybe the system itself, if you look at it as say web server, right, web server is sometimes you request a server, right, some HTTP message is sent, you expect a response back from the server. The server could either give you a response or the server could simply not respond at all because it is overwhelmed or it is down currently, right. So but unlikely you will get a different web page if you go to a server, right. So it depends on the service that you have to look at and see which of these outcomes are possible. But in the case of network accepting a packet, you can deliver the packet correctly to the destination, which is here part 1, or it could be delivered but still because of errors, right, you might be delivering an incorrect packet to the destination, that is possible, right. Errors are introduced in here, somewhere in the system some errors have happened, right. And the third is the router has simply dropped the packet. So these are sort of three. So depending on which of these happens, we have again sub classification of metrics, okay. So if a packet is indeed delivered correctly, right, then we look at sort of three metrics, okay. So I would say 1A is delay or response time. So I made a request, what is the response time of the system, when did this request get satisfied. So that is your first metric. We know that the packet is very easy, I sent it, when did it get delivered, I send a courier by speed post, when does it get delivered, right. So that is that. So this is a user specific metric, right, what did this user see, what did I see in terms of response time. Then from the system perspective I would like to know how many packets per second am I able to deliver, right, that is representing the capacity of the system. So that is usually throughput or rate. So that is in some service requests per second, right, that is to capture. The third would be resource utilization. The resource could be many things, right? CPU, cycles consumed, memory, or bandwidth consumed, etc. So during this, for example, I am sending several packets on a link. Utilization of the link, is it 50%, 100%? For the same load, if I am able to use the resources less, then that is better, right? Or when I am running a searching algorithm, sorting algorithm, if I use less memory, that is better. So you look at resource utilization as another way of capturing, right? So if you might be able to get the same delay, same response time, or same throughput, right? But if one system uses less memory than the other, then that is better, right? So utilization of resources is less in this particular system. So that is what, so these three would happen whenever the service is being done correctly, right? So service is done, therefore I am more interested in one of these three. Of course other things are also possible, variance of this, right? So these are the high level metrics, and within this we would say whether it is mean or mean plus variance and things like that. So that is the first category, right? Then the second category is when something gets done incorrectly, right? So a simple thing is packet gets delivered, but there are errors in the packet, right? Corrupted packet is being delivered. So we would like to know, right, what is the, well, I would say 2a probability of error. And this probability of error is easy. If you look at bit error rate, that is simply that metric, right? Bit error rate is simply what is the probability that a bit will get corrupted when it is sent on a link. Or packet error rate, when a packet traverses multiple links, what happens? What is the effective packet error rate? So therefore, those are metrics that will capture the probability of error, right? And sort of related to this, on some systems they also say what is the mean time to, or mean time between, or mean time to error, right? So this will tell you how long the system will function typically, right, correctly before errors take place. Let us say for 100 milliseconds there will be no errors, and then an error will take place, and every 100 milliseconds there is an error. So this might be possible to compute, might not be possible to compute, but that is another way of looking at the system character of this metric characterization. Mean time, that will be in the case of a system, yes, yeah. So if a system fails, so there will usually come under reliability. Yeah, this is, yeah, mean time to repair is also there, but on a link that is kind of not there. Because these are transient errors, right? They kind of come and go, they are not fixable errors, right? But if it is a system that goes down, that will come under more availability of the system, right? The third part is when something is your requested is not at all done, right? So not done can be, in the case of networks it is simple, what is the packet drop rate, right? How often does this happen? Or it could be something, right? So this is usually called as speed, reliability, and the third category is availability. So availability depending on what system it is, right? The common metric that we would see is like the mean time to failure. This is true of machinery, where we say what is the mean time to failure, then the mean time to repair also comes in, but that is not the behavior of the system itself, right? That is like a separate process. The repairing process is independent. You simply take this machine off the shop and get it repaired elsewhere. Or in the case of networks and so on, right, it is usually the packet loss rate, right, is something that will capture the fraction of packets that are dropped, they are not serviced at all, right. This is loss in the sense of dropped packets because buffers are full. It is not because of link errors, it is because the buffer was full, it was dropped by the system, therefore system load is very high, right, or the system did some random RED kind of algorithm which dropped packets along the way. And then within each of these metrics I can have mean, like I said, variance and all the moments that I want, right, but that is the high level. And then one more categorization of metrics is whether they are global versus local. So global metrics would be something, for example, right, and let us look at throughput. This earlier example we saw, there is an Aloha system, or there is a router, right, that is sharing packets, right, that is servicing packets from several queues. So if I represent a queue like this, right, there are several users sending packets to this queue. This is a queue. So packets are buffered here. So that is a buffer, that is your server. Packets are entering from different sources. Okay. So as a global metric, what can you think of? Global in the sense of system level. I would say instead of global, book system global, system level metric. What is system level metric? So the throughput, right? Throughput utilization. So from at this, I can say how many packets per second are being delivered by this server. That is throughput. And the second is utilization. How often is the server being utilized, right? Is it 10%, 20%, 50%, and so on. So those are system level metrics. Now if you spend the money to install a server, you want those to be high. You want the throughput to be high because you are able to service more customers, right? So you want to put faster server. You also want to keep the server busy most of the time, right? Because you are paying this installing the server and so on. So you want utilization to be very high. So from that perspective, I want to keep these two numbers as very high, right? Throughput as well as utilization. But from the user perspective, which is important? Delay, right? Response time. I don't care if others get serviced or not. My packet should go through first. I should be able to go. People do that, right? You stand in line, they always come in front of the line and just try to jump you, right? So that is so therefore they only care about response time. So the user's time, one thing is response time, and the second is from a throughput perspective, I want my fair share of throughput, right? So the fairness is also an important consideration. So if I say that the system, let's say, had 3 users, we saw this in networks, right? If the total throughput is 15 packets per second and user 1 had 13 and user 2 had 1 and user 3 had 1, right? That is not fair. But system is very happy because it is able to service 15 packets per second. System capacity is 18 packets per second. System has been wonderfully serving everybody, right? Or at least in terms of number of packets per second, system has been able to reach this to a very high number. But in terms of, you look at fairness, then it is not fair. So there is disparity in the amount of service that is being given to the different customers. So therefore when you try to design a system, you have to see which of these metrics you have to measure, right? So simply reporting total throughput will be misleading if there is this big discrepancy, and this also happens sometimes in simulation. Sometimes you never pick a packet from a particular connection for different, you had your some metric to compute and this ended up not selecting a source at all, in which case this is unfair. So from the user perspective this is important, system perspective this is important. So you have to look at a system. If this is not at all important to you, it does not matter, right? These are all VIP connections, therefore they will indeed get more connection, that is different. But if you are interested in fairness, then you should also measure these other metrics. You should not simply stop with total throughput as the only metric of the system itself, right? Okay. Okay. Yeah. So it depends upon the impact of those metrics on the system, right? So in the case of packet delay, mean is alone not adequate, right? We all probably know that, because variance also matters. Variance in terms of range, right? What is the range of, if I tell you that your packets are going to be having delays from 1 millisecond to 5 seconds, right? Very long range and delays, and you are watching a video and so on, then your video caching or video buffering algorithm, right, has to buffer almost that much amount of, right, 5 seconds worth of data has to be buffered, and therefore it adversely affects you. Or if you do not have that kind of buffering, then what happens is packets will start, right? You will have a packet, then no packet for a long time, another packet, so your video will be very jumpy, right? So it really depends upon how it impacts the application, and that is again coming from the intuition of the expert who is looking at the system. In some cases it really does not matter, in some cases it would indeed matter, right? So throughput, if you look at throughput of a user, right, measured over various points in time, if that varies a lot, if that could be like, let's say over every 10 seconds I measure the throughput and I always get 1 kbps, right, throughout those 10-second intervals, then the user does not care. If it suddenly goes to 10 and comes down to 0.5 and so on, the user might not, if the user does not notice anything differently, that the delay observed does not vary as much, then it does not really matter. So usually for some metrics you look at second, third moments and so on, but most of the times we simply look at mean. Of course not only mean, we will look at this much later on, you can also look at your regular arithmetic mean or something like a geometric mean, harmonic mean, right. All those things also come into play depending on which system it is. Sometimes some of these will make more sense. For example, ratios comparison, you might not want to do a simple arithmetic mean, but like some other mean will be more useful, or even median mode, right. All those things also remember from your basics of probability, right, or statistics. So sometimes there is also median mode. Those are things that are harder to compute with a mathematical model, but easier to compute with a simulation model. So it really depends on that.